let's extend on that basic idea of growth and decay. So what we do is to take into account some external conditions, and the classic example, given the temperature today, is not a bad example, is temperature. And if you've got an object that's cooling down, then when it's cooling down, it'll never go lower than the temperature of the surroundings. So if we were to pull something out of a fridge and sit it here now, and say the room temperature is, I don't know, what do you reckon it is? About 30? Okay, let's just say it's 30 for argument's sake. It doesn't matter how long it sits here, it'll never rise, because it'll warm up in that case if we're taking it out of the fridge, it'll never rise above 30. Without any other external conditions being put on it. That's the basic idea. So the equation changes. So effectively what it's doing is, if you think about before, we just had a basic exponential, which always goes asymptotic to 0. So now we basically need to shift the curve up, down to whatever that external temperature or external condition is. So hence our equation to P to T, our differential equation, instead of just being K times P, it becomes K times P minus N. And I won't go through and derive it this time, but similar idea to before, you turn it upside down, become a log function, and so on. The solution, there's actually two solutions. The first one we don't worry about. It's what's called a trivial case. And if you look at it, if P was equal to N, the derivative would end up being 0. So it's just saying there's no change. And so P would always be N no matter what. So that's a trivial possibility. The one we're interested in, and the one we would write down, would be this one. So as I say, it's our exponential curve, but it's been shifted up to N, whatever that external condition is. So P represents the population at time t. N plus A will become the initial population, because if you were to sub in t equals 0 there, you'd get N plus A. K, once again, is your growth or decay constant. T, again, is time. So that's how we've modified it, to take it into account some sort of external condition. And the classic ones is the temperature, and you see these ones a lot. Newton's law of cooling, it's known. He's responsible for such a lot, that Newton. I suppose there was no telly. What else did he have to do but come up with formulas and theorems? So T is the temperature inside the room at time t. A is the outside air temperature. And the law of cooling states that its rate of temperature is proportional to T minus A. So we're going to show that T equals A plus CE to the KT satisfies that formula. So in other words, we need to be able to show that it'll be dt, won't it? D capital T, d little t, unfortunate choice of pronumerals, is proportional to T minus A. So let's start with T equals A plus CE to the KT. We will differentiate and get dt, and that is KCE to the KT, because remember A is a constant, so when we differentiate that we get 0. But we know that T minus A is CE to the KT. That's just a rearrangement of the formula we started with. Move the A to the other side. So if I substitute that in for CE to the KT, I get K times T minus A. So in other words, it's proportional to T minus A, and that's what we wanted to prove. So okay, this formula does satisfy. And so what you'll find is it'll be one of two things. They'll actually ask you a question like this to show that it satisfies. If they don't ask you, then it's okay to assume it. And we'll just assume that it does. Alright, so now we're going to solve a problem. Outside air temperature 5 degrees Celsius, so we must be in winter, unlike right now. Heating system breakdown causes the inside temperature to drop from 20 to 17, and it takes half an hour to do that. We want to know how many hours until the temperature comes down to 10 degrees. So in this case, T will equal 5 plus CE to the KT. Right, so remember that 5 is the external condition that it won't go past. So in this case, the 5 degrees. So when we work that out, then C must be 15, right? Because C plus 5 would be the initial temperature. So we now have t equals 5 plus 15e. We can now work out the growth constant by subbing in after half an hour, so 0.5 in this case, because we're dealing with hours. T is 17. Rearranging our equation, and eventually we get k is 2 log 12 on 15. So now let's solve the problem. We want to know, when is that temperature going to be 10? So 10 will be 5 plus 15e to the kt. Subbing in, remember that k I've stored in my calculator to save me using the approximation. And we get 1 on k, whatever that number is, times the log of a third. Turns out to be 2.4616, and so on. It's said after how many hours. I'm going to say 2.5 rather than say 3. I mean, 2.46 so close to 2.5. But again, it's probably a good reason why you write your whole calculator answer down before you make your conclusion, especially when you're talking about things like time, and if you're saying hours or minutes or what have you, at least they can see that, yeah, you did the calculations, you've got the right amount. Alright, well that's all I really want to say about that. So it's just an extension to the basic problem where we've shifted the curve up or down depending on what that outside influence is.